Good afternoon all. Welcome to our 3-day second session AICTE ATAL-FDP program. Today as eminent speaker we have with us Dr. Siddhartha Sankar Thakur, Professor NIT Durgapur, West Bengal. May I have the honor to read his biodata. Dr. S.S. Thakur received B.Tech in Electrical Engineering in 1985 and M.Tech in Power System in 1989 from the RE College Durgapur, which is presently known as NIT Durgapur. He obtained his PhD from the IIT Kharagpur in 2000. Dr. Thakur has over 30 years of teaching and research experience, and presently he is working as professor at Department of Electrical Engineering, NIT Durgapur. His research interest includes PMU application in power system state estimation, dynamic state estimation, etc. He has published more than 40 international peer-reviewed renowned journal papers and several reputed conference papers. He has served various academic positions like Dean, Faculty Welfare, Registrar at NIT Durgapur. He has authored and co-authored 10 book chapters and 3 books. Many students have got doctoral degree under his supervision, and presently 3 students are pursuing PhD under his guidance. He has served as the reviewer of various reputed journals from IEEE, Elsevier, Springer, etc. Thank you, sir. Now, please. Sir.
Good afternoon, everybody.
Good afternoon, sir.
Thank you. So we start our topic today. It's power system state estimation and introduction to false data injection attack on it. If we see, the main objective of any electrical power utility is to ensure reliable and stable supply economically to the consumers. Accordingly, proper monitoring, operation and control of the system is very, very important. This is accomplished at the energy control centers using state estimators. It is nothing but extracting the system states, that is the complex phases at the buses of the system from the redundant power system measurements, which are not only redundant but also erroneous in nature. Certainly, the nature of topology is to be known. Once we know voltage phasors at all the buses, all electrical quantities of interest, including the ones those are not measured, that we can compute and that can be used for security constraint dispatch and control of the system. It is of two types, static state estimation and dynamic state estimation. If we think of the fundamentals, that is load flow studies, what did we do there? There also we found out the state vectors at the buses, that is voltage magnitude and phase angle at all the buses. But that was an offline study, because in case of load flow studies, things are stored in our computer, like system information, that is line data, as well as load and generation data. Those are stored in the computer. As and when necessary, we can go for the load flow studies. It is basically done. Load flow study is basically done for system monitoring the system operation, enhancement of the system operation, and for near future loads that can be gathered from the system. But once again I repeat it, it's an offline study because things are stored in our system and we extract the state vectors as and when necessary. But it is an online process. It is an online process where system information available from the system measuring instruments at a particular sampling period. We use these measured quantities to extract the state vectors. Although it has already become a full-fledged workforce, the solution algorithm, bad data detection and identification, observability analysis, topological error analysis, etc., all other are there. We already done it, but still research is going on, particularly with the introduction of PMUs, in the system. So, in static state estimation, what we get? We get the state vector at the present instant of time when our measurements are available. On the contrary, a dynamic state estimation is nothing but a tool that utilizes basically the extended Kalman filter, which not only provides the state vector at the present time state, but also gives a prediction of it for the next time state. What we get from this advantage? We get from this, from the state vector at the present time instant, we can go for calculation of all other electrical quantities that are needed for operation and control at present time instant. And from the predicted state vector, we can find out the predicted measurements. So predictive analysis, predictive security constraint, predictive operation and control, those things can be done. So if we know that how our system is going to behave, so accordingly we can take preventive measures if needed at any time. However, this dynamic state estimation, it has mathematical complexity and also time consuming. So that requires more and more research on it. The foremost aim of static state estimation is to provide the correct estimate of the voltage pressures at all the buses at present time instant using this measurement model. This is the measurement model. This is the measured vector, which is m-dimensional measured vector. Phi x is nothing but m-dimensional power flow equations. Eta is the noise vector of dimension n. Why eta is there? It is uncertainty in the measurement present. State vector is having a dimension of, if there are n number of buses, then number of state vectors will be 2n minus 1, and this measurement uncertainty eta is modeled by Gaussian zero mean Gaussian noise having these properties. This is the mean value is 0 and its covariance matrix, that is measurement error covariance matrix is R. In the commonly used method is the W weighted least square method, or in short WLS approach, where we minimize this objective function to get an iterative solution, that is starting with some x, starting with some initial value of xk. We go on correcting it using this equation, where H is the Jacobian matrix, this is the covariance matrix, and delta zk is nothing but the measured value minus the calculated value. So once we get delta xk, we update the state vector this way, xk plus delta k, that gives the updated value. Here k is nothing but iteration vector, iteration count. And this iterative process continues till delta xk becomes less than the specified tolerance. On the contrary, in dynamic state estimation, we have two linear models. One measurement model is this: zk is equal to phi n of xk plus eta k at time instant k, and this is the system dynamical model x of k plus 1, that is, here k is represent the time state at a time instant, sampling time. So x of k plus 1 is equal to fk xk plus uk plus wk. Fk is time instant, and also when this product is added with the some known control action, we say that is x of k plus 1. And certainly this wk represent an uncertainty in the model. Both of eta k and wk, they maintain, they are assumed as zero mean Gaussian noise. They are uncorrelated. Uncorrelated means neither of these two are related with each of them in any way. These are their statistical properties as already stated. Their mean values are zeros, zero mean Gaussian noise, and this is the measurement error covariance matrix, and this is corresponding to modeling error covariance matrix. Since they are uncorrelated, so this is zero. In case of dynamic state estimation, we have this objective function. The first component is similar to that we had in weighted least square method, but there is a second component that acts as fictitious measurement, that is, this acts as fictitious measurement. What is k? K already I have stated. It is the time state or sampling time. So based on measurements of k minus 1, x of k by k minus 1 means it is the predicted state based on k minus 1 information. So when we minimize this, that leads to this, that is state vector at present time instant based on measurement at present time instant. We get it like this. It is the prediction based on earlier measurement or earlier time state, and this is known as Kalman filter gain, and zk minus this is your calculated value. And this gain matrix, Kalman filter gain, is calculated like this: sigma k by k hk transpose into rk inverse. So what here this particular term is known as filtering error covariance matrix. This is computed in next equation, that is this filtering error covariance matrix. So what we do, we calculate the filtering error covariance matrix first, then substitute that in equation 15. This is a Jacobian matrix, RK is known, so Kalman filter gain is known. So we can find out the prediction, we can find out the filtered value from equation 14. So flow of the equation is like this. First we go for 16, calculation of filtering error covariance matrix, then the Kalman filtering gain in equation 15, then we go for calculation of the state vector at the or estimated vector at the present time instant using equation 14. Then at the prediction state, This is the state transition matrix. When that is being multiplied by the state vector at present time instant and added with the known control action, we get the prediction at k plus 1 time state using the information at k, and corresponding corresponding prediction error covariance matrix is computed like this. That is Fk sigma k by k, Fk transpose power plus, this is the modeling error covariance matrix. So first we go for the filtering, then we go for the once filtering is over, this component is available with us. So this is also known control action, that is also known to us. Accordingly we can find out the predicted state vector at time step k plus 1 and corresponding covariance matrix we can calculate from equation 18. That is about the basic fundamentals of static state estimation and dynamic state estimation. However, both of these, the existing methods, they use nonlinear filtering techniques. That's why the solutions obtained from these methods are suboptimal. Because in this case, what we do, we go for Taylor series expansion of the functions, and as we do in case of Newton action load flow. What do we do? Second and higher order terms of the Taylor series expansion we neglect. Same mathematics is also used here. So when you are neglecting something, so solution will be suboptimal. It cannot be. What I am going to discuss now, that will give you optimal solution, because straight away equations are solved. No suboptimality due to Taylor series expansion. That means these filters will give you explicit solutions. So they are optimal in nature. So two algorithms we discuss. Recently we have worked on this. That is optimal static state estimation and optimal dynamic state estimation, including new data detection, bad data detection, identification, and correction method. Correction method, why? Because the methods that are usually followed in the literature, they first of all find out the bad data, detect, then identify presence of bad data, then that particular bad data is identified. Thereafter, it is excluded from the measurement step. Say you are having 100 number of measurements, from which 2 measurements are found to be bad. 2 measurements are found to be bad. That is, we have detected and identified 2 measurements as bad data. So from the 100 measurement stack, we exclude those 2 measurements. But unfortunately, what can happen in certain cases, the system may become unobservable, because the data that we are excluding, they are containing some system information. Those information are lost. So it may so happen we may not be able to find out the state vectors at some of the buses. But when this correction method is employed, the system always remains observable, because we are not excluding the bad data, rather we are modifying it, we are correcting it, so that state estimation can continue. No scope for loss of observability occurs. This optimal in this novel, so together that becomes NSSC. Algorithm is formulated on a linear measurement model. Earlier the measurement model that we used, they are non-linear in nature. Now we are having linear measurement model relating the complex measurements directly obtained from optimally placed PMUs with the complex voltages. From the PMU, what measurements do you get? Wherever it is located, we get the complex voltage and the complex line currents. Complex currents flowing through the lines which are connected to that particular bus. So we are going to use these PMU measurements directly. So this is the linear measurement model, where, as I said, from the PMUs we get line current measurements and the voltage, complex bus voltages. So the Z contains complex line currents and the sub-vector complex bus voltages, which come directly from the PMU. Now here lambda is nothing but the observation matrix corresponding to this IL and VB, lambda 1, lambda 2. So submatrix lambda 1 consists of complex line admittances and lambda 2 is an identity matrix, because when this one is VB, that is bus voltage measurements, and here also is B, so it has to be identity matrix. Lambda 2 has to be identity matrix. And finally, this is a complex random variable with the characteristics of Gaussian noise, that is white noise, having zero mean, and it will have some covariance matrix that you will find. Then the two subvectors zeta 1 and zeta 2 of the corresponding to the lambda 1, say it is for the line current, its mean value is 0 and its covariance is phi 1, that is found out from the variances of the real part and the imaginary part. It will be a diagonal matrix, that's why that. Similarly, we can find out the covariance matrix phi 2 in a similar manner against the complex bus voltage measurements. So if phi 1 and phi 2 are the covariance matrices, error covariance matrices corresponding to zeta 1 and zeta 2, in that case overall covariance matrix phi is phi 1 phi 2, that will be that. Then it can be computed. Earlier what we are doing, we are finding out delta x. Now directly we are finding out voltage V. So there is no iteration. That's why it is optimal solution. That's why it is optimal filtering. So V is nothing but some G inverse lambda transpose phi inverse Z. What are these quantities that we will find? The G is designated as gain matrix. It is calculated as lambda T. What is lambda? Lambda is what? Observation matrix, that is known to us. This is overall error covariance matrix, that is also known to us. So G can be computed directly. Then once we know the G, so G inverse, this is your observation matrix transpose, and this is your covariance matrix inverse, and Z is your measurement already having. So from equation 23 directly we can find out the complex voltage V without any iteration using the optimally placed PMUs. That's why it is optimal solution. So this is the flow chart. As you can understand, system data will be read first, then lambda 1 and lambda 2, then we calculate the G. Once G is known, G inverse is found out, then directly solve for V. It is not, and certainly Z comes this way. Linear measurements received from optimally allocated PMUs. Then we go for detection and identification and correction of measurements if needed. So that Z comes over here and we find out the value of V. There is no iterative process, so it is optimal solution. Similarly, when DAC, we go for the direct DAC, it has, as I said, two steps: filtering step and prediction step. At the prediction step, we know the model x of k plus 1 is equal to fk xk plus some uk plus some modeling uncertainty. At the filtering step, we will use optimal Kalman filter, the way we have used just now, and in the prediction step, we are using Brown's triple exponential splitting method to track the real-time evolution of power system dynamics very closely. So equation remains same as we did in case of as we did in case of statics in SSC. And in this case we find out the covariance matrix first. This is your filtering error covariance matrix, where lambda is known, phi is known. So once again lambda it is known. So this is your prediction error covariance matrix, it is known. So that gives us sigma k by k. We substitute the sigma k by k in equation 27 to determine g k by k, and then we substitute that in equation 26, where we have the estimated value at time instant k. We are directly using the complex voltages for the prediction step. So we are writing it in the complex voltage form. That is Vk plus 1 is equal to Fk, Vk plus Uk plus Wk. This is your state transition matrix, no control action as usual, and this is Gaussian noise, zero mean with some covariance matrix Mk, and its values of Mk is nothing but a diagonal matrix, because errors that occur in the various states, they are uncorrelated. Accordingly, it is, each term in the diagonal will be addition of variances of real part and imaginary part. So we will be using Brown's triple exponential smoothing method to determine the forecasting. When exponential smoothing methods are used, various levels of exponential smoothing are possible. It may be single exponential smoothing, double exponential smoothing, and triple exponential smoothing. Single exponential smoothing is applied when the data is having a particular trend, when the data follows a typical trend. When the data follows square or cubic form, then we can go for, as needed, we can go for double exponential smoothing or triple exponential smoothing. We have tried both of them for the power system dynamics, but we found that Brown's triple exponential smoothing is working above the double exponential smoothing method. Accordingly, we have applied, and this is the value for first exponential smoothing. 1 stands for first exponential smoothing, 2 stands for second exponential smoothing, and 3 stands for third exponential smoothing. So 3 exponential smoothings will take place one after another, and that's how we find out the coefficients A, B, C to determine the predicted value like this, given by equation 38. So if we see the flow chart, we read the system data, we as usually construct the lambda matrix or observation matrix comprising of lambda 1, lambda 2 corresponding to POV line current measurements and POV voltage, complex voltage measurements. Then we construct, once we know this lambda, we calculate this lambda transpose phi inverse lambda. Then the filtering error covariance matrix is computed. Then we can compute the column filter gain, and then we finally go for the estimated states at present time state. Here we once again read the linear measurement, that is complex line currents and complex voltage at the buses from the PMUs. Necessary detection, identification and correction of measurements is done here in this block. Then the Z enters here. So thereafter we go for the prediction of the state vector, that is complex voltage at the buses, corresponding error covariance matrix, and that with a delay that goes back here to this block for further filtering process. So in both these the methods that we have discussed, they use linear equations. Both the methods, NSSC and NDSC, they use linear measurement model. That's why linear measurement model. That's why the filtering done by with the NSSC and NDSC, they are optimal in nature because we are having explicit solution. If we compare with the basics, there you will find, if you recollect, X is corrected by delta X. But here we are getting directly the complex voltages. Furthermore, these methods reduce the computational time because in normal case, the real and imaginary parts are treated separately, or the bus voltage magnitude and phase angles are separately treated as state vectors. Whereas in this case, directly we are using the complex voltage and buses. That's why sizes of the matrix becomes hard. So wherever matrix inversion taking place and multiplication taking place, we are saving computation time. That's why electron will see computation time is much less for these schemes. Then bad data processing, we use some pre-estimation technique, that is, before the estimation takes place, we detect and identify the bad data. In this approach, the measurement that corresponds to largest normalized residual is treated as anomaly or bad data. Now, as I said, correcting bad data instead of elimination provides a distinct advantage to keep the system always observable. Because whenever we eliminate, now in normal procedure is to detect, identify and eliminate the bad data, but that can make system observable. But correction of bad data always keeps the system observable. So what we do, first we find out the normalized residual. How do we get that? First we calculate this deviation, that is, this R residual is equal to Z, this is your measured value, minus this is your calculated value. This residual we first find out, and corresponding covariance we find out. So this ratio gives you the normalized residual. Now this normalized residual, when that is greater than 3, it is treated as bad data. Why greater than, why 3 is used? If you recollect normal distribution, how is it? In the vertical direction, what do we plot? We plot the probability density function. In the horizontal direction, we plot the variable for which we are giving the probability density function. So it starts from normal, or in other words, directly in normal distribution, it takes place from minus 3 sigma to plus 3 sigma. Now in normal distribution, it starts from minus 3 sigma to plus 3 sigma. So anything above 3 sigma, or when, as it is normalized, so anything above 3, that will be treated as bad data because there is more than 3 outside the distribution. So as the maximum value of normalized distribution is greater than 3, it is treated as bad data. Then correction is, then we, using this equation 42, we correct the bad data, where we have this one, this lambda is defined by this particular term, we calculate, and it is the corrected value, corrected bad measurement, and the ZB is the actual bad measurement, and this is the estimated value of the bad measurement. So using this mathematics, that is equation 43, we correct the bad data, so that instead of eliminating it, we are correcting it. Furthermore, although sometimes we may find this one is greater than 3, it can have 2 reasons: presence of bad data, and another can be sudden change of load variation. If the load suddenly varies, in that case also we may find that this normalized residual, maximum value of the normalized residual is more than 3. So we need to discriminate these two events. So we find out this particular thing. We go for a mathematics 43 to discriminate this where mu3k is the third moment of the discrimination and sigma k is the standard deviation of the distribution at k plus k time state. If the index exceeds pre-specified value, that is this one, the maximum value of this one, if that exceeds a tolerance or pre-specified value, then it is a normal load change, sudden load change. So with this mathematics, what we are doing, first we are finding out, we are discriminating whether it is a sudden load change or bad data. If it is bad data, then we correct the bad data using the mathematics of 42. So that our system always remains observable and state estimation continues. Both the methodologies we have applied on IEEE 14 bars, 30 bars, 57 bars, 118 bars, and also on two practical Indian systems, DBC 38 bus system and Northern Regional Power Grid, that is NRPG 246 bus systems under both normal and anomalous data condition. Now, for describing the load variation, we have considered a typical IEEE system that gives the load variation in a system throughout the day of a year. All the years are specified in a year. All week values are given, and weekdays are also given. Corresponding loads are also given. So you can select any week in a year, and correspondingly you can go for selection of a particular day. That's what we have done. We have considered, from that we have used 10th week of the year, which has 73.7% of load demand of annual peak demand, and we have opted for Monday, which gives 93% of the load demand of weekly peak load. We have assumed constant power factor is constant. If power factor is constant, in that case reactive power also follows the active power. Now, when loads are changing in the buses, correspondingly generations are to change as well. So how does that happen? That happens using the participation factors. You must be knowing what is participation factor. Participation factor of generators in a system. Say for example, system load is 100 megawatt. You are having three generators. One generator is serving 50 megawatt, another generator is serving 30 megawatt, and third generator is serving 20 megawatt. So that 100 megawatt load is shared amongst these three generators this way. Now, if the load, say for example, comes down to 50 megawatt, how these generators will share? They will share in the same proportion, the way they were doing for 100 megawatt load. Now they will share 25, 15 and 10. That is participation factor. So, using the generator's participation factor, whatever system loads are changing, that is being shared by the generators. Once we know system information is known to us, then loads and generations are also known to us, then what do? We go for load flow studies to find out the state variables at each time step. Load flow studies at each time step we can find out, because that will give you the true states, true values. Because in load flow we know the whatever result we get from load flow, that is true values. Now we are simulating using these true state vector obtained from the load flow to calculate the POV measurements. We calculate the POV measurements using these state vectors, that is voltage measurements are already directly obtained from the load flow solutions, and line currents we calculate using these two values of the load flow. When that is done, we add with this an error which has distribution of zero mean and standard deviation of 0.5%. Normally the scatter measurements are having error of the order of 2% of standard deviation, but POVs are further accurate. Accordingly, the standard deviations are much less. In this case, we are considering 0.5%. So thereafter, some bad data are simulated. Bad data of 15 sigma. 15 sigma are simulated like this. Line current in the line connected between bus number 9 and 14. It occurs at 12th time instant. A single bad data. Similarly, this is multiple bad data having two bad data occurring at the same time. Line current connected between buses 2 and 5. This is between 2 and 4. It occurs at 18 times sample. Similarly, bad data for 30 bars, 57 bars, 118 bars, and DBC 30 bus system and NRPG 248 bus system are given here. Then assessment result is to be assessed and it is to be determined how the results are coming. For that purpose, some performance indices are found out. Say for filtering state, we find out average absolute filter state error, filtering state error or filter state error, and from the information output at filtering state, we find out the J index. J index it is very important because it basically depends on the ratio of estimated value minus true value, measured value minus true value. Since estimation is better than the measured value, so what will happen? See, in both the cases, numerator and denominator, we are having true values. Since the estimated value is less than the measured value, so J index is supposed to be less than 1. So we will see, and then also we are having maximum absolute filter state error and maximum absolute predicted state error at the prediction state. Then some statistical parameters also we are finding out. Maximum mean square error we find out. We maximum standard deviation of error, maximum sum of square error, because in all these cases these error values have to be less, so that we can prove that the system of proposed method is working well. The statistical parameters for predicted states we also can calculate in a similar way. The way we are doing for the filter states, same way we are doing. Some results we are having. See, for filter state, as I said, for 24-hour load, corresponding to 24-hour loads, we are calculating the real power at bus number 91 of 118 bus stage system. What we find there, see, both your NSAC and NDAC, they are optimal solutions. So their results coincide. They are optimal results. So NSAC, NDAC, they coincide together. See, this is the result. They are coinciding because both of them are optimal solutions, and see, they are, and this is your true value, this sky color. So they are pretty close to the true value, whereas other methods are away from the true value. You see other methods, they are away from the true value. This is further understood from the second one, where at bus number 191 for NRPG 246 bus system, if we see there, this is the true value, and both NSAC and NDAC, they are closer to the true value, whereas the other methods, they are further away from the true value. So certainly from this we can say that these two methods, NSAC and NDAC, they are working better. Similarly, here we have J index. As I said, J index has to be less than 1. If we see the J index for both NSAC and NDAC, they are coinciding once again, and they are situated at lower position compared to the extended Kalman filter and weighted least square methods. So performance is better for both NSAC, that is linear estimators. They are working better. and average absolute state error, if we see, filter state error, if we see, they are further down compared to the other two methods, that is EKF and SSE. It is further illustrated this way. In both the case, in this case also we find that maximum average filtered state error, there also this NDAC and SSE, that is linear methods, are working better because they are optimal solutions. Some more results for average absolute filter state error. See here, once again if we see NSSE and NDAC, they are situated here, whereas SSE and EKF, they are then above these. So errors of the proposed scheme is less. Here we have the comparison of active power, real power at 118 bars. First number 118 IEEE 118 bars test system. If we come for the statistical parameters, if we see that they at the top it is given for NSSE and NDAC. These are errors, statistical parameters of the errors. So smaller the values, better is the result. So what we find, since both NSSE and NDAC, both of them are optimal, accordingly what we find, their results are coinciding. Their results are coinciding and their values are less compared to SSE, that is weighted discard method, and EK. Similarly, for other systems, if we see for 30 bus system as well as 57 bus system, if we see their values are less. For the predicted states, if we see, here we have shown three methods. Double exponential smoothing method holds two parameters: double exponential smoothing, Brown's double exponential smoothing, and Brown's triple exponential smoothing. Comparing these three methods, we find the method that we have used, that is Brown's triple exponential smoothing, having least error amongst all these. Similarly, for the same thing is executed by the 30 bus test system, 57 bus, 118 bus, DBC 38 bus system, and NRPG 246 bus test system. So what we have found? We have found that statistical parameters for both filter state and prediction state, both are less for the linear estimators as well as, that is NSSE and NDAC, and here also for the Brown's triple exponential smoothing method, they are having least error statistics. Some more results, if we see here at the predicted state, predicted active power consumed for bus number 29 of 57 bus system, there you find true value is the sky colored one, and BT is this, BT is bit closer to this compared to the other two methods. Once again, if we see true value and BT, they are closer. If you see, they are closer. At the predicted state, maximum average predicted state error, there also you see error is less for the BT, it is situated below the other two. State errors, once again if we see statistical parameters of predicted states for all the test states, if we see, that the BT is least, Now if we consider the bad data has been incorporated as time step 12. Now, what is shown here in this diagram is that this I1 you see, without bad data detection, if we go for estimation, certainly J index becomes more. When the bad data with bad data detected and identified and eliminated, bad data is eliminated, then the J index reduces below a little, and when the bad data is successfully detected, identified and corrected, we find this is the characteristic where it is least, that is J index is least. That means detection, identification and correction method is working above the two. Time, computation time, if we see, for 14 bus system, NSCC is taking this multiplied by 10 to the minus 3 millisecond, that means 4.928 millisecond, and this one NDS is 5.121 millisecond, whereas the other two popular methods they are taking more time. Similarly, if we see the two methods NSSC and NDSC, they are taking lesser time compared to SSC and DK for all the test systems and practical systems. Now, the PMUs are very costly indeed. Placement of PMU may be of the order of placement of one PMU may be of the order of $34,000, $35,000, like that, in dollars. Multiply that by 80, you'll understand how much it will be in Indian currency. So, allocation of PMU at each optimal location is not feasible. So, what do? We use PMU measurement as well as SCADA measurements. So, we are going to discuss a novel method of DSC that uses both these measurements. That's why it is known as hybrid. A novel hybrid dynamic state estimator. And at the prediction step, once again we will be using the BT method. At the filtering stage, it implies a linear relationship between the complex hybrid measurements and the complex states. As I said, it uses both SCADA measurement model and PMU measurement model. For the SCADA measurement model, we use the element voltage vector. What is element voltage in a power system? Element voltage in a power system is nothing but the voltage drop across the lines. Voltage drop across the lines is termed as element voltage. So that is element voltage, say a particular line, voltage drop across a particular line at time instant t is equal to the difference of the two voltages where this line is connected. That is, if bus I and J are connected by a line, then that element voltage is determined by the difference of bus voltage at ith bus and voltage at jth bus. Then this equation 52, we can write it this way. This element voltage, now you see, for one line it is this. When you are writing in vector matrix form, so element voltage vector is nothing but a vector, observation vector, multiplied by the complex voltage vector. This matrix which comprises 0, 1 and minus 1. Because if we see for this one, what will be the what will be the coefficients? It will be plus 1, this one, for this one it will be minus 1. Accordingly, we are having plus 1, minus 1, and wherever buses are not connected, it will be zeros. And so, equation 53 we define as the SCADA measurement model. So, SCADA measurement we are using to find out EK. Now, how to get this EK? We get it from the active and power flow, active and reactive power flow of the system. This is a complex power flow, that is active power and reactive power, and conjugate of that is taken, divide that by the voltage, that gives you the current, and this is the current. This term stands for the current leaking through the half line charging. So this is the current flowing through the line impedance between the two buses. If we multiply that by the series impedance of the line, that gives you the voltage drop across the line. So that's how we calculate the element voltages, and equation 53 is our SCADA measurement model. For the once again, for the PMU measurement model, as I said, two measurements are there. For that is line currents and the bus voltages. Correspondingly, two sub-vectors are there. When that is multiplied by Vk, that gives us the PMU measurement vector. Now see this one. As I said, PMU measurements are nothing but line currents and voltage. So hybrid measurement model we can write like this. Well, what is Zk? Zk is nothing but this is Ek. Ek corresponding to the element voltage measurements, and Zk PMU is nothing but this. So three sub-vectors are there. One stands for the element voltages, then the second one is for the line currents, and third one is the bus voltages. Correspondingly, the sub-matrices are there comprising of line admittance. This is also for line admittance, and this is, as I said, +1, -1 and zeros. The covariance matrix we need to calculate. That covariance matrix is calculated for this covariance matrix for the element voltages is calculated like this, and this is the covariance matrix for the PMU measurements. So overall covariance matrix will be this. This is for the SCADA measurement, and this is for the PMU measurement. So once again we are using linear measurement. Once again we are using linear measurement model, although it is hybrid, that is both SCADA measurements and PMU measurements are used in it. So that ultimately, since linear measurement, accordingly we can calculate the filter state like this. First we calculate the filtering area covariance matrix. This is the coefficient matrix, we know what it is. This is the covariance matrix, already we have calculated in 61, and this is your prediction error covariance matrix. So this is also known to you. So inverse of that gives you Pk by Ke, that is estimated value. So if we substitute that here, and this is known to you, coefficient matrix, this Rk is known to you, you have calculated that in 61. So Kalman filter gain you have calculated. Then this is your Zk, this is your Zk, this is your Zk, this is your Zk. Accordingly, state vector at present time instant we find out from equation 62. So flow of equations will be 64 followed by 63 and then 62. Once again, simulations we have done for similar simulations we have used. This is the variation of active power using and comparison is made between the true value Ek, extended Kalman filter, and NHDAC. It is more explicit here. Where we find the NHDAC is closer to the true values. Reactive power calculated using NHDAC is closer to the true values compared to the extended Kalman filter. This is real power calculation at bus number 29 of 57 bus. There also the same thing exhibited that NHDC is closer to the true values. Average absolute filter state error there we find. Error is less for NHDC. Say once again, J index if we see this hybrid method gives you less J index. This is average absolute filter state error for 15 bus 57 bus system. This is for NHDC and this is for EK. So these are some of the characteristics, error characteristics, performance depicting performance of the NHDC. If we see the statistics for two systems, the result is given 14 and 57 bars. If we see the values respective systems, that is and respective methods, then this is for EK, this is for NHDC. For NHDC it is much less. Execution time also if we see NHDC is having lesser time of computation. So what we have established is that in a system it is not necessary to deploy PMUs at every location. Rather, the existing SCADA methods, SCADA measurements also we can use along with the PMUs that you are presenting. We are deploying in the system, and using that we can go for NHD. Although I have shown you NHDC, certainly you can go for NHSC, SSC, that is static state estimator. Also this similar way you can use, because the measurement model will remain same. Now what we have done, we have shown, when is the break for you?
3:15.
3:15. So shall we meet after this? Go for a break.
Yes, sir.
We go for a break, 15 minutes of break, then we will continue. After this I will introduce it. This one, thereafter I will go for FDI, that is cyber attack on systems. That will be rather a new topic on which many of you can extend your work. Only a few literatures are there. So as FDI when I discuss some of the aspects, just an introduction I will give you, so that you may find interesting in that, to work in that field. Fine. So we are meeting after 15 minutes. Fine. So distribution of power system noise, oftenly we usually consider to be Gaussian model, but certainly sometimes when bad data is present we call that to be heavier tails, and we call presence of bad data is designated by outliers. In presence of bad data or outliers, performance of both static state estimation, dynamic state estimation decrease or degrade, because they use weighted least square and EK, extended carbon filtering technique, which are very vulnerable to bad data or outliers. So accordingly, robust filters are needed to be designed accordingly, and a robust estimation, robust static state estimator, and a novel robust hybrid dynamic state estimator are going to be discussed, and along with that we will see how does it work, and it does not require any bad data processing mechanism. It is actually obtained by combining maximum likelihood estimator or ME estimator with NSSC method. Already NSSC method we have discussed, so we need to discuss the ME estimator in short. Concept of ME estimator approach, also known as maximum likelihood estimator, which minimizes an objective function. This is the objective function that is minimized. where R is nothing but R Z minus lambda V. This is the residual. This is the residual, and the Z is defined by this. So this R, it is the residual function is this, which is minimized by the M estimator, which finally gives, in short I am saying, because it will take, if I discuss in detail, the M estimator, that will take time, that's why directly I am giving you the results. This M estimator formally modifies the gain matrix this way. Earlier we had here R inverse, instead it is this term where it is calculated like this. When normalized residual, that is Ri divided by sigma, the corresponding standard deviation, that is less than a threshold, we say it is 1 by sigma square. We say 1 by sigma square. If it is more than this, in that case, it is this. The threshold divided by Ri, sigma I, and sign of Ri is there. So it is a threshold value. What we are doing is that means if the normalized residual is more than a pre-specified tolerance, we are comparing in the tolerance is B threshold. For this purpose, we have used 1.5 and we can go it up to 3. Although we have used in this work 1.5, we can go up to 3 because as we know that error statistics is distributed from minus 3 sigma to plus 3 sigma. Accordingly, we can go this threshold up to 3, but for this work we have used is as 1.5. So using this covariance, error covariance matrix, we write the new robust statistical estimator like this. That means what we are doing, we are truncating. We are truncating the extra value. Rather than eliminating, we are truncating that extra value to particular this value when it exceeds, when the normalized residual exceeds the threshold value, we truncate it and give this value. In this case also system always remains observable, and this is the estimated value. We will see the flowchart of it. We go for observation matrix lambda construct it as usual what we did earlier, lambda 1, lambda 2, then measurement residual we find out R, and then we find out the diagonal matrix using equation 75. Then we go for the computation of this gain matrix from 74, and then we go for the estimation from equation 76. It ends. We take the complex measurement from the optimal place PMUs comprising outliers. That means in this case we are not rejecting the outliers, rather we are processing it to a value, particular value, comparing it with the threshold, so that system always remains observable. The bad measurements of 15 sigma we have incorporated at various time instants like this. We will see the effects of it. If we see the effect of it, particularly in this case of Jane days, this is the one. NRSSE is this, and this one is NSSE, which does not have any bad data processing, and this one is NSSE with bad data processing, separate bad data processing, and M estimator is this. Since J index at the instant of bad data occurrence, that is at instant 3, and same we find is going down. Similarly at this instance it is going down. So what we can say that this NR SSE is acting better than the other two. Similarly, if we see average absolute filter state error, there also this particular scheme is working well. All these are showing good results for NRSSE. Once again, comparison of error statistics of average absolute filter state error for 180 bus test system. Maximum average filter state error in both these cases. NRSSE is working better. If we see the statistical parameters for 57 bus system, there we find NRSSE is having least values of error statistics. Similarly, for 118 bus test system, NRSSE is having least error statistics. Similarly, when we go for using the same method, only thing is that in place of R, we are having this matrix. So as usual, we calculate the filtering error covariance matrix first, using which we go for calculation of the carbon filter gain. Then we go for calculation of the filtered states at present time instant, Vk by k. Here also we see that when at B54 at real time instant bed measurement comes of 15 sigma. These are the bed measurements occurring at real time instant, and here it is occurring at 12 and 18 time instant. We'll see what happens at 12 time instant. If we see J index for NRH DSC is going down, whereas others are having higher values. Similarly, at time instant 18, you see NRH DSC is less than the other values, so it's acting well, acting better than the other two. Similarly, for other things, that is average absolute filter state error, if you see, in all these cases NRH DSC is acting better. We see in all these cases, we find NRH HDSC is acting better than the others. You see this black one which is representing. Similarly for NRPT 246 bus stage system, there also you find on occurrence of bad data at time is at 12 and 18, it's working better than the other two because G index goes down. Average absolute state error, filter state error, there also you find it's doing well. Maximum absolute filter state error, there also you find it's working well. Statistical parameters, if we go, it is having least values. For all the statistical error parameters for all this 57, 118, 246 bus system. So we have shown that now this one is detection and impact assessment of false data injection attack on power systems by the researchers recently. So you can also work on this particular thing. If you do so, certainly you will have plenty of evidence for that. Fault data injection attack is such type of attack which means altering stored or transmitted data. That means in a system, many data are stored like system data are stored with you, system information are stored with you, and also some data, that is measurement data, transmitted to the energy control centers, that can be altered by this false data injection attack. That means The false data injection attack may cause alteration of the data stored in the computer and as well as the data that are transmitted to the energy control centers. It can be aimed against the data communication infrastructure, data stores in the control centers, in the SCADA remote terminal units. From the SCADA measurements when you are connecting, that also can get affected. Physics literatures focus on various detection techniques for filtering out injected false data on the traditional SCADA system based on nonlinear estimators. But in recent research suggests that PMU measurements are also vulnerable to cyber attacks. Not only the SCADA systems, PMU measurements can also be attacked by these cyber attacks. Accordingly, this work focuses on detecting false data attacks in PMU assisted linear power system state estimator, even for successive time samples, which is not yet considered by anyone so far. That means, even if it continues for successive time states, false data injection attack, it can be detected. This detection method, what does it do? It monitors the changes in the complex PMU measurements between the current time instant, the present time instant, what is the value, and one step previous day, one step previous time instant. That means today if you are monitoring the kth time instant, then yes, today is what? Today is Wednesday. So Wednesday, this time instant k and previous one step previous time instant, that is time step k minus 1 previous time instant on Tuesday, one day before. Then whatever variation we are getting, it is compared with the variation of the forecasted measurements. That means we are picking up today's measurement at this time instant and yesterday's measurement at k minus 1 time instant. This whatever variation we are getting for the same time steps, for the same days, we take the forecasted measurements. Whatever variation is there, that all we compare with that. A particular distance known as Manhattan distance is used to calculate the distance between the two distributions of the measurement variations. So, whatever measurement variation we are having here, then the variation that we are getting for the forecasted measurements, we are trying to find out the numerical distance between these two distributions. In the event of a FDIA, that is false data injection attack, this distance will increase significantly from normal conditions. So this comparison gives us, in the case of FDIA, this comparison will give higher value, so that we understand yes, FDIA has occurred. This approach, its effectiveness has been evaluated by applying it to 14 bus and 118 IEEE 118 bus stage systems we have applied. If we see some mathematical background is needed to understand the process, false data injection, data injection attack process. This was presented in this reference I will give you in the end. It shows that an attacker can steal the false data, thereby inject it. If the attacker knows the system structure, the system information has to be known by the attacker, and also he can manipulate multiple measurements at the same time. Then only injection can take place. Injection can take place if the system information and the attacker can manipulate multiple measurements at the same time, then FDIA will occur. The generated false data injection attack can skip the bad data detection mechanism. See, mechanism, it can, you are having your bad data mechanism installed in your computer through which you can find out, but this particular FDIA is such that sometimes it evades the system, that bad data detection mechanism cannot catch it. if we say that attack vector is A, then if that A is equal to H is a Jacobian matrix, what is C error? It is the error that will occur in the state estimation if the attack is there. With the attack measurements, if we go for state estimation, whatever error that will occur, we call that C error. If that is multiplied with H, we call that is the attack vector. A is the malicious data injected into actual measurements, and C error is the injected state estimation error, as I said. Now the tempered measurements will be what? This is the tempered measurement, that is equal to measured value plus the attack vector A, Zn plus A. After false data incorporation, the estimated state also comprises of error, that is with the attack vector A. If we go for state estimation, that we this is for normal state estimation, that we error that will come. Now, as I said, when this condition is satisfied, your bad data detection mechanism cannot identify it. That's what we are going to see next. That is, traditional bad data detection technique is unable to detect false data injection attack, as the measurement residual remains intact. That is, if this condition is satisfied, then bad data detection mechanism cannot identify FDIA. Why so? We will see. So with the attack, if we call this is the measurement residual. What is measurement residual? That is equal to Z attack vector. After the attack, whatever measurement vector is there, this is that minus A Jacobian matrix into X and X ATT attack vector. So that is the measurement residual after attack has taken place. This ZATT can be written like this. ZATT is what? Already we have written. ZATT is equal to Zn plus A. Zn plus A minus H into what is XTT? XTT is this here. After simplification, what do we get? We get Zn minus HH. What it is? It is the measurement without data, and this is the calculated value of the measurement. So it is nothing but the normal residual. So if this condition is satisfied, in that case, the residual what is obtained, even if the FDIA has occurred, false data injection attack has occurred, residual remains same. That is why your bad data detection technique is unable to find out whether FDIA has taken place or not. So develop methodology. Develop detection method is an online detection technique that tracks the alteration of measurement. What I said, the current measurement at the current time instant K, and each is measurement at K minus 1th instant. Whatever variation is there from the PMU, that we see, and we compare this variation with the forecasted measurement at the same time instance. Then this Manhattan distance is used to quantify the distance between the two distributions of measurement variations. That is, actual measurement from PMU at time instant K, and yesterday's measurement at K minus 1th instant from the PMU. This difference is compared with the difference forecasted at the same forecasted difference of the at same time instance. Numerical value we have to find out, quantitative value we are trying to find out what is the distance between these two distributions. We assume alpha variation is the distribution of measurement variation derived from real-time measurement. That means this one, alpha variance VAR is nothing but the change in the value, today's value and yesterday's value at k minus time instant, and beta var is the variation derived from historical data or forecasted measurements. Then what we can write, alpha variation is equal to this is C. It is measured today at time instant k, and it is measured in previous day at time instant k minus 1. So that is alpha variation, and beta variation is what? Same. What only thing is that it is forecasted measurements. Now the deviation of these two different measurements variation can be mathematically expressed as the mathematical variation. We are trying to quantify the difference of the two using the Manhattan distance. It is equal to the one norm of the distance between the two vectors, Manhattan distance between any two vectors. If we have two vectors x and y, that can be written mathematically like this, sigma x minus y. Call it like this. So considering the above formula, Manhattan distance delta can be mathematically determined as, so in place of x we are writing this, in place of y we are writing this, and if there are n number of measurements, it will be I is equal to 1 to n. What it is doing actually, Manhattan distance of two vectors x and y, by definition what it is nothing but the difference of the real parts of the two vectors and difference of the imaginary parts of the two vectors, then we add them up. So if there are n number of measurements, so we have to sum them up. So I is equal to 1 minus n. I is equal to 1 to n. Same thing we are writing. This is your alpha var, and this is your and alpha var and beta var. When you substitute, it appears like this. N is the total number of measurements during any data perturbation or distribution in the power system. Power system measurements, P value will become more than that of normal conditions. Whatever value of P comes during normal condition, if any perturbation is there, certainly P will increase. As a result, if the P value is greater than at any instant, if we find P is more, in that case certainly we can suspect that FDIA has occurred. We see the algorithm starting with we obtain the PUV measurements at current time instant of present day. Certainly at the same time we are also collecting the historical days data also. We calculate the variation of the real time measurements alpha var from 84. Then we calculate the historical from the historical measurement we find out the beta var. We calculate the difference alpha var minus beta var at this stage at this block. Then we can find out the P dist at this block. If P dist is high, we say yes, FDIA has occurred. We need to mitigate that FDIA. If it is not, then no FDIA. So we are taking help of earlier results to detect FDIA. Simulation details have been performed by varying the load, as I said. IEEE reliability test system, as I said, it gives us 52 weeks load variation with every individual day's load For this simulation, we have assumed 9 week. We have taken Thursday is taken at the present date, which is 96% of the peak load of the weekly peak load, and previous day is the Wednesday. Certainly, when it is Thursday, it will be Wednesday when the load is 98% of the load of the weekly peak load. We have once again assumed constant power factors for reactive power, followed the active power counterpart. Change in the load was distributed among the generators corresponding to participation factors. We have done for successive load flows for true values. Then simulated measurements we have obtained using Gaussian noise of 0 mean and standard deviation of 0.5%, and we have used IEEE 14 bus and IEEE 118 bus test systems to verify the methodology. We see in next we show a diagram of IEEE 14 bus test system which allocates 4 PMUs. These are the 4 PMUs we have shown, 2, 6, 7 and 9. So optimal location PMUs are there. We are going for performance evaluation. For that part, some indices are there. We define false positive rate as what? It is false positive rate occurs by detection technique, detection attack. Even when there is none. That means although there is no FDIA, but it detects an attack. We call it false. It is a false detection. False positive. A false positive rate is expressed mathematically like this. False positive rate is equal to false positive divided by false positive plus true negative. It is for the true negative. Actually, it hasn't occurred. So, number of cases, true negative, that is there. False negative rate, when the detection technique fails to detect an attack, that means attack was there, but it has failed to detect the attack. This is referred to as a false negative. So, false negative rate is this, false negative divided by false negative plus true positive. And finally, true positive rate. True positive rate is defined as true positive divided by true positive plus Fn. False negative. With these indices, we will see attack states are these. For IEEE 14 bus system, X9, 12 and 13, and magnitude of the attack has been varied from 1% to 10%. Similarly, in 118 bus system, it is at bus number 12 the complex phasor, and at bus number 18 the complex phasor. Once again, magnitude of the attack was varied from 1% to 10%. We have simulated the attack magnitude. This disturbance has occurred deliberately at time 5 to 7. Sorry. Yes, 5, 6, 7. These are the 3 time steps where this attack has occurred. If we find, we have given attack magnitude of 2%, for which if we see P distance, that is Manhattan distance, we find high for time steps 5, 6 and 7. We calculate 5, 6, 7 where attack has taken place, where we have simulated the attack. We find the Manhattan distance to be high at this instance, whereas at other instance where there is no attack, it is pretty low. Now we have increased the magnitude of the attack to 5%. At the same IEEE 14 bus system, during the same time steps 5, 6 and 7, we see once again P dist value becomes more. Now you see, since the attack attack magnitude has increased from 2% to 5%. So value of P dist, if you see, it has now increased. You see it was this value about 0.7. Now you see it is about 1.75 like that for the time step P. If we further increase the attack magnitude to 10%, once again we find the P dist, that is Manhattan distance, is more. So FDIA, the method proposed, that is method shown that successfully detects the attack, FDIA attack on the system as P dist value during these 3 time steps, successive time steps is more. If we see the false positive rate, if we see detection threshold, as long as if it is low, false positive rate is high, but if the detection threshold increases, we find it becomes negligibly small or zero. True positive rate, if we see, attack magnitude is increasing. Beyond this point, you see it is 1 because it cannot exceed 1, so it has assumed the maximum value. For 118 bus test system, if we see, 118 bus test system, if we see, once again, during time steps 5, 6 and 7, if you see, FDI has occurred, it is distinctly seen from this that at 2% attack on 118 bus test system, on bus number 112 and bus number 118, we see P dist value is more. When the attack magnitude increases to 5%, we see once again P dist value is becoming this. It is more still, it is further has increased, but still it is determining the presence of FDIA. Attack magnitude goes to 10%. Then we find once again it has been detected by the proposed method, the method that is shown. So P dist value during this period is about 5. So in the attack magnitude, as the attack magnitude increases, P dist value also increases, determining presence of FDIA. It is high, but thereafter, as the detection threshold increases, it reduces. And true positive rate, if we see, with the attack magnitude vary, as the attack magnitude varies, it assumes 1 always, even from 1%. What is the impact that we see from the system voltage? Bus number 9 at 14 bus test system, if we see, bus number 9 was one of the affected buses where the measurement was tampered. We see without FDIA is this guy, that means when FDIA is not there, no attack is there, it goes normally like this, voltage magnitude, and true value is this. Now due to presence of FDIA, the voltage magnitude has increased to such a level during time steps 5, 6, 7. During time steps 5, 6, 7, if you see, FDIA has occurred, so voltage magnitude at this particular bus, that is bus number 9 of IEEE 14 bus test system, it has increased. If we see the phase angle, respective phase angle, we see during the time steps 5, 6, 7, once again we see it is more than the normal. So these are the impacts of FDIA. Once again, bus number 12 was another bus where attack was there. We simulated the attack. So during the same time steps 5, 6, 7, what we find? We find the voltage profile has gone up from the normal. This is your normal. the true value, and this is without FDIA. So during 5, 6, 7 it has increased. At the same bars, if we see, at the same bars, if we see the phase angle, that has also increased during the time steps 5, 6 and 6 and 7. For 112 bar system, if we see once again at during 5, 6, 7, voltage magnitude has increased to a great extent. Similarly, phase angles, if we see during the time steps 5, 6, 7, it has increased. And this is for voltage magnitude for 118 bar system, IEEE 118 bar system at bus number 118. If we see the voltage profile is this, it has gone up during the time steps 5, 6, 7. Correspondingly, if we see the phase angles, they are also up during time steps 5, 6 and 7. So that's all. And these are the references that I have followed. Some of the references I am having. Not all, only something like 47 included in this. So that's all for this. So what's the time now? Hope I have completed within 4:15. So if you have any, we have time for some exams any period, you can ask questions. If some question comes in your mind, you can go for it. So thank you. So you tell me if you have any question in your mind, we can discuss that. Or we call it over. See, there are some more methods that you can go for finding out the exact buses where this has occurred. That I was, although I have shown you that presence of, I will get back to some of these the last slides, presence of FDIA, etc. See, presence of FDIA and others that are detected by this method, but there are still some pending works that you can go for finding out the buses at which directly. In this case, we know where the perturbation has taken place because we have simulated the system. We know that bus number this, we have perturbed the data. That's why we can show it. But still, some works you can go for, that is how to find out the buses where this perturbation took place. Detection and identifying the buses, those methods you can go for. Okay. This is relatively a new topic where not much of work has taken place. So if any of you interested, you can go for this. We know that this has happened in 14 bus system. Presence of FDIA I have shown. Similarly, the voltage profiles when I am showing, we know yes, this bus number 9 was perturbed, so voltage profile is increased, but you have to find out, methods may be developed for finding out the exact buses, exactly locating the exact buses where it happened. Those methodologies you can go for. Okay. So if any of you having any question in your mind, please feel free to ask me so that your query is answered, or I'll stop here. If any of you want this copy of this, certainly I have no hesitation in giving you this. So later on you can go through this. So sir, what shall you do? Shall you stop? Any question?